Morning everyone, we'll be starting class into 1 to 2 minutes time. Hi, good morning everyone, and the lectures that we're going to be doing this week in particular are going to be focused on the Z transform and its uses and practicality. This first lecture is going to be showing us why it is that the Z transform is important, as well as how it can be used in its own Z domain and how this can be represented graphically as well. We'll have to backtrack a little bit to understand why it is that the Z transform is required and why it is that we cannot use the Laplace transform for discretized time signals as well in this lecture. So we know that when you're dealing with continuous time systems, the way to describe them are using by differential equations. And if you try to solve a differential equation, you either do direct integration, Laplace transform, or some sort of power series solution. And we've already covered these extensively in previous courses that we've done throughout the degree. And in watching the role of the Laplace transform, where we have the complex operator S here is equal to common omega plus, common whatever this letter is plus j omega, sigma, all right? So the sigma part represents the real part of the S operator is the amplitude change with the decay of growth, and the omega part represents the signal frequency. And we're going to observe why it is that this S operator here does not work well for discretized time systems in a little bit. So in solving for any continuous time differential equation using the Laplace transform, it was possible for us to get a set of values to develop some sort of circuitry where the equations themselves can be mapped back to resistors, capacitors, op amps, and basically it would just be an analog filter equation that we obtained, where we had some sort of amplitude and phase response as well as some transient and steady state response altogether. So that's for the continuous time case, but for the discretized time case, we wouldn't get like a nice fancy differential equation. We will get like a sequence of values represented by a one-dimensional vector, which gives us the desired response which we are required to obtain in the discretized time case. Now, the reason why the Laplace transform doesn't work well with sample signals here is that let's watch this Laplace transform of this cosine signal in general. We know if we use the Laplace transform table, we can get the equivalent transform fit in the S domain here. And we're going to be examining this if we switch this to a sample signal. So when we factor out the denominator here, this being s plus j omega k, s minus j omega k. That means we're going to have a pair of poles around that omega k factor. When we sample this cosine signal from continuous time into discretized time, mean that we'll have some sample and frequency mapped back to omega s. It means that for every instance of omega s and omega k, they're going to be repeated complementary components. So there's going to be for like 1 omega s or 1 omega k and 2 omega s, 2 omega k, and so forth as we keep on going. And this also reflects on the negative side of the axis as well. So we have positive positive omega s and negative omega s, and positive omega k and negative omega k. And we saw this in particular when it is that we did the associated Fourier transform for any signal, where once we obtained the spectrum of the signal, if it was periodic in nature, there was a positive frequency and a negative frequency. So we see the same effect here for the Laplace transform. Remember, the Laplace transform and Fourier transform are very similar in nature, with just a few key differences. Each instance here where we have an n omega s and an n omega k, this is going to be spectrum replication, which we saw in a few lectures back, where for every instance of omega s and omega k, the spectrum itself will be replicated throughout the entire series in the frequency domain. So what happens is that once we sample our cosine signal from continuous time into discretized time, and if we try to apply the Laplace transform, that means because it's going to be n omega s and n omega k, we want to end up with an infinite number of poles, which is not practical. So that means that the Laplace transform itself won't work well for sample data, because it's going to be creating a whole set of infinite number of poles and zeros. And in trying to find out what's going to be a different tool for making this mapping of the infinite poles onto a finite set of poles instead, and zeros, some brilliant guy came up with the Z transform here, where they said Z is equal to the exponent of st here, where t was just going to be the sampling period, s is going to be the Laplace transform coefficient, and z is going to be what we're going to be calculating for. In defining the Z transform, given by this definition here in the blue block, the formula that they came up with was the x of z formula here is equal to the summation between positive infinity and negative infinity of x of ktz to the negative k. Now, this version here was in between positive and negative infinity is what we refer to as the two-sided Z transform. However, because we're dealing with causal signals, we're only going to be dealing with the one-sided Z transform, so where k goes from 0 to positive infinity. The right-hand side of the equation basically remains the same here regardless. The only thing that is different is the limits that determines if it's two-sided or one-sided. So, like I said, we're mostly going to be using the one-sided Z transform throughout the entire course. And yes, the Z component here is a complex quantity, and if we expand this out in a little bit, we're going to see that this is going to be a power series in Z or in negative powers of Z because of Z in minus k. And we're going to see what this looks like in the Z plane in a little bit. Then expand out the x of Z series here. You can see here basically, as we keep on going, it's literally going to just be a power series throughout the entire thing because of that summation series here. So it can be also rewritten such that we move all the Z components to the denominator instead, which basically is the same thing as well. Either representation is fine. But what we need to observe is what this is going to look like graphically instead of mathematically. So because we're going to say for the S component, we're going to put the real part here, sigma is going to be 0 value. And we're going to put in that S component here where Z is equal to e to the power plus minus j omega t here. If we remember that this here is being a complex coefficient because of the Euler expansion, where this is going to be cosine j omega t minus plus minus sine, no, sorry, cosine omega t. Let me write this down so that way you guys can see what the expansion is. So e j theta, where theta could be omega t, is equal to cosine theta plus minus here, plus minus j sine theta. And if you remember from this Euler expansion here, that's basically going to be a phasor with magnitude 1 and with phase omega t, because of the theta value here, where theta is equal to omega t. And let's say if we had different values for omega here, which is going to map back to our sampling frequency. So let's say if we're in instances of 8 of the sampling frequency, we see here that for when we calculate for the phase, it's basically just going to be a rotating phasor, where we say 360 degrees divided by the 8 components, giving us 45-degree increments as we keep on going. And this is very similar to the total factor that we saw in our previous lectures. So in mapping our infinite number of poles from the S-plane here onto the Z-plane, if we had a pole here directly at the center, this maps to a phasor with magnitude 1 and angle 0 degrees into the Z-plane. If we had an impulse here, or any sort of line, vertical line here in the S-plane, this will map to a circle in the Z-plane, where the radius of the circle is going to be the magnitude of this impulse. If this impulse here has a magnitude of 1, the circle here with radius 1 is referred to as the unit circle in the Z-plane. So mathematically, what that means is that j omega axis in S domain is going to be mapped onto the unit circle in an anti-clockwise direction. And we consider the real S-plane axis, where we put back in our sigma components, and we expand out the Euler expansion. All but basically we see here is that for anything that is e to the minus sigma t, with the same phase and so forth, because sigma here is negative in nature, that means when we try to calculate out for what's going to be what we refer to as the region of convergence for this equation, the magnitude of z is going to be less than 1, which is literally going to be anything inside the unit circle is going to map to the exponent of minus sigma t here in general. So if we go back to what this means here, is like, let's say if everything on the left hand side of the plane here is mapped by this negative sigma here, graphically that means everything inside the unit circle is going to be mapped accordingly. And this also brings us back to a case of stability with the Laplace transform. We know that for a system that needs to be stable in the Laplace domain, all the poles need to lie onto the left hand side of the Laplace domain. Transforming this into the Z domain, that means for a stable discretized time system, all the poles must lie within the unit circle in the Z domain instead. Similarly, if the right hand side here was shaded instead of the left hand side in the Z domain, what that means is that we'll be shading outside of the unit circle instead. So that's basically what I just now said. The right hand S-plane will map outside the unit circle, and a stable system has Z-plane values inside the unit circle. So if the S-plane is separated by our sampling frequency here, omega s, and we put that into our Z equation where z was equal to e to the minus st and so forth. And we keep on going, and we expand this out accordingly. We see basically that we impose a period of 2 pi regardless because of that omega s that we've introduced. And that brings us back to the discretized time property for discretized signals, where once we impose any sampling frequency upon a continuous time signal, we basically impose a period of 2 pi upon it, regardless of what the value of omega s here is going to be in general. So in doing the mathematical manipulation here, we see here that for omega plus omega s of t, this is going to just be omega t plus 2 pi in general. And because that's 2 pi, that means we just get back to the same signal accordingly, because the signal repeats itself every 2 pi cycles. So what this means is that, in general, the infinite set of poles and zeros on the S domain will just map to the finite set of z-plane points because of that unit circle that we just saw. So let's go back to the one-sided z-transform equation that we just now saw a few slides previously. And we saw here that basically this one-sided z-transform was the power series in z. It is quite possible that that z-transform there is not going to converge for all values of z. And we're going to see how do we calculate for the region of convergence using the z-transform. So let's start with a simple equation for x of kt here, which is basically going to be our discretized time unit step. So for everything k is 0 to positive, we're going to have a value of 1. For everything k that's negative, we're just going to have a value of 0. Let's plug this into our z-transform equation, which was basically the summation series between k equals 0 to positive infinity of x of kt, or x of k here instead of negative k. X of k here, because it's going between 0 and positive infinity by our equation, is just going to be 1. So when we plug this in, we just have the z to the negative k part here in our summation series. And if we expand this out, we'll see it's going to be 1 plus z to the negative 1 plus z to the negative 2, keep on going in negative powers of z. Now, what this basically is a geometric progression from mathematics, where the geometric progression equation for a summation series, where we're trying to figure out what it's going to be convergent to, and we'll say GP here is equal to the summation between k equals 0, positive infinity of e r to the k. This just basically converges to e divided by 1 minus r, where the magnitude of r here is going to be less than 1. So that's basically the geometric progression formula that you're going to have to use in particular for evaluating any power series in general. And as of such, you can see here that our A component in our summation series is just 1. Our R component here is going to be Z, and the K component here is going to be negative K as we keep on going. So when we converge this is going to be A divided by 1 minus R. A here is just 1. And we just know what R is. R here is going to be the Z to the negative power that we needed. So that's going to be Z to the minus 1 here in general in doing the convergence. Now, because we use the GP here, in the geometric progression formula, we also got the region of convergence immediately where the magnitude of R needs to be less than 1. But we need to prove this in general. So in order to prove this using the summation series here, we watch such that because it's negative powers of Z, we say that the denominator here being 1 minus z to the negative 1 needs to be more than 0. And because we're dealing with magnitudes of z, because z here is a complex component, we're going to say, okay, let's just take the modulus of z to the negative 1. So that means minus z to the negative 1 here is going to be more than negative 1. And if we flip the signs, remember when we flip the signs here, this 1 sign is going to change to the left hand side. So that's going to be magnitude of z to the negative 1 here is going to be less than 1, which satisfies our equation for the region of convergence, mapping back to our geometric progression. So, just to reiterate, the convergence is such that the magnitude of z to the negative 1 is going to be less than 1. And we saw that here via the mathematical proof, where we let the denominator for x of z here be more than 0. And we solve for the magnitude of z to the negative 1 accordingly in this inequality. Because both sides of the equation here were negative, when we transform this into positive, this more than sign will change to the less than sign. So just remember that once we change any sign on the left and right hand side accordingly for any inequality, the sign of the inequality will change as well. The reason why we take the magnitude of z to the negative 1, because remember, the z component here is still complex in nature. So in evaluating the region of convergence, we always take the magnitude of the z component regardless. Let's say if we rearrange this such that this was in positive powers of z, the same thing holds where we just let the denominator here be more than 0. So to calculate for the region of convergence here, we'd still do the same thing, where we say magnitude of z minus 1 is more than 0, so magnitude of z here is just going to be more than 1. So the question is, what is this going to look like in our z domain? So we have our unit circle here for our z plane, and we know that z, the magnitude of z equal 1 is just going to be the circle here with radius 1 giving us our unit circle in the z domain. But magnitude of z being more than 1 is going to be everything outside the unit circle that we're going to be shading. If there was magnitude of z less than 1, we'll be shading inside the unit circle only. So the region of convergence, depending on what the magnitude of z is going to be, more than 1 or less than 1 accordingly, or any certain value, will determine which parts you're going to be shading in your z domain. So I'm just going to give you guys an idea of what's going to happen if we didn't have a value of 1 here. So let's say if we had magnitude of z here being less than 0.5, and let's say I'm just going to draw my z domain plot here. What this means here is that I'm going to have a circle in the z domain centered about the origin, where this radius here r here is going to be equal to 0.5. And because magnitude of z here is going to be less than 0.5, that means that we're going to be shading everything inside our circle here with radius 0.5. So depending on the value that the inequality takes, be it 1, 2, 3, 0.5, 0.6, 0.7, this is going to determine the radius of our circle. In this case, because we had 1, we have a radius of this circle here centered about the origin, where the radius value here is going to be that value of 1. And if it's more than or less than, if it's more than, we shade outside the circle. If it's less than, we shade inside the circle accordingly. Now comparing our unit step in the S-plane here to the discretized time unit step in the Z-plane, What that means is that for the continuous time unit step, because it's on the right hand side of the S-plane here, where we see that there's going to be positive values of sigma, and mapping that to the Z-plane, we just shade everything outside our unit circle here, where the circle here has a radius of 1. Alright. So that brings us to the end of our Z Transform 1 lecture. Are there any particular questions at this point in time? Yes, the questions on the Z transform will be very similar to that what you'll see in signals and systems. It's just basically because it's applicable to DSP, we just doing a refresher of it from signals and systems in particular. Because, like I said, the Z transform is used in particular for discretized time signals. So yes, the questions are going to be very similar to that what you've seen in signals and systems. That being said, however, once we reach like problem set 3 and whatnot in particular, we have all these Z domain equations, you will see like how to go about solving for each one of them in turn. So like you'll see, okay, when you're encountered with a different type of Z transform equation, what's going to be the strategy for going about solving it in particular, and how we can apply that strategy for any similar type of Z transform equation that you encounter. Alright, doesn't look like we have any further questions at this point in time. Alright, so let me close this off. I just want to check how long the second lecture is going to be. Second lecture is that, third lecture is that. Okay, alright, so Alright, well, we'll leave the second and third lectures for the Wednesday session in particular. They're not very long in nature. They should be pretty much okay. If I do start the second lecture at this point in time, I will end up stopping like halfway through, so it doesn't make sense to start it right now. Alright, so what we saw in today's lecture, just recapping, is the introduction of the Z transform and how did we go about formulating it for use with its discretized time signals. We also saw how it can be represented graphically by mapping the infinite number of poles and zeros from the S-plane into the finite number of poles and zeros onto the Z-plane. We also saw that the difference between the S-plane and the Z-plane is that the S-plane was represented in Cartesian coordinates, whereas the Z-plane here was represented by polar coordinates given by the radius of the circle and the angle at which the phasor rotated around in the Z-plane itself. Well, we also saw in particular that depending on the region of convergence for the Z-plane, this determines the radius of the circle, as well as if we're going to be shading outside or inside the circle, such that if it was more than 1 in this particular case, we'll be shading outside the circle, but if it was less than 1, we'll be shading inside the circle to represent our region of convergence. Finally, we also saw that in calculating for the region of convergence, we need to make sure that we use our geometric progression equation that we saw here in slide 19. I'm going to just bring this back up here. We need our geometric progression equation here for our summation series here to obtain a finite equation accordingly for the entire summation series using our geometric progression formula. And to obtain the geometric progression formula, once we had our equation here, we just let the denominator here be more than 0 and we calculate for our region of convergence for our Z component. The only thing to pay attention to is that if we had negative signs on both sides, or if we were changing the signs on either one of these sides, the inequality sign here will also change as a result. So this more than here changed to a less than as of the result. Even when we are dealing with positive powers of Z and calculating for the region of convergence, the same thing holds true. We just let the denominator here be more than 0 and we just solve for Z accordingly in the inequality. Right. So Wednesday's lecture, we're going to be focusing more on the Z transform and how it can be used for different sorts of problems. So in particular, how do we go about using it for solving what we refer to as open form and closed form solutions, as well as how do we use the Z transform to solve for difference equations, which is basically the discretized time version of differential equations instead. Also, don't forget to vote on which problems gave you the most trouble for problems at 2A and 2B, because after we finish those lectures on Wednesday, we're going to be moving straight into the problem sets themselves and doing the solutions live, depending on which 3 problems gave you guys the most the most trouble in general. Alright, so until Wednesday, take care, be safe, and I will see you guys soon. Later. The midterm currently is scheduled for, I believe it's going to be the 3rd of March. If it changes to the 10th of March, I will let you guys know. But so far, it's been scheduled for the 3rd of March. Alright, see you guys later.